Hello, everybody. This is my pleasure to describe to you what I believe is a new topic, very exciting topic, that is connecting the recent results of astrophysics with the result in chemistry on the topic of the origin of life. So let's start with the astrophysics perspective and in a way the incentive for this talk. Well, the picture that I'm showing you right now, it's a real picture that is obtained using what we call radio telescopes combined together, which is essentially the thermal emission of a very early star producing a temperature of the order of 50 K at an age for the star of about 10 million years, that is showing a structure that we call a proto-planetary disk. This structure is the origin of planets. What you do have when you form stars is a lot of stuff remaining around due to the conservation of the angular momentum is kind of adopting the structure, and the structure is in a way interacting by itself and producing a lot of interesting dynamics that is producing this kind of grooves you see there. And inside the structure there are building blocks that is assembling each other, making small core of material that becomes at some point heavy enough to attract by gravity all the material around. This is how we understand the formations of planetary systems. We have now quite a lot of this kind of picture. We trying to address the formations in a kind of general sense of planet in the universe. Now, on the other hand, from the stage of the formations, we reach another milestone, that is the discovery of planet. And it's fair to say that it has been a surprising adventure based on the fact that everybody had the picture of the solar system as the archetype of all planets in the universe. And actually connecting the formation stage that you do see here with the reality of the product, if you want, of a planetary system is not something we understand well enough. But we have to acknowledge that there are a high diversity of planetary system existing. To give you a general outlook, what we have found so far, this is two diagrams that just displaying every dot here. It's a real data point of a planet for which we have obtained a direct measurements of the size or the radius. This is expressed here in Earth size radius. We essentially see planet from 1 Earth radius to a bit more than 10 to 20 Earth radius. You see Jupiter to help you a little bit where it stands against the period. On the right axis, you have not the radius, but you have the mass of the planet. This is essentially what we can retrieve using two techniques. One of them is called the transiting techniques. We just see the planet going in front of the stars. We retrieve the size of the planet. The other one is the Doppler techniques, which is sensing the mass of the planet, and we retrieve the mass of the planet, and against the period as well. And you do see on this picture that the planet that we have detected looks quite different from the one we have in the solar system if you compare with Jupiter and the Earth that we have here. And that was essentially the big surprise that I was describing to you. Now, what is interesting with this picture is if you add a little more of reading by adding what we call the threshold of detection, so we cannot detect all the planets we want. We are somewhat limited still in the discoveries because the planets are small. They produce small effects on the stars, and there's a point where we just don't see the planet. And you see when looking at the size of the transit, there is a limitation. So we have failed essentially to detect Earth twin planet. We have Earth-sized planet clearly here. We have planet within the period or the orbit of the Earth, but clearly nothing really exactly like the Earth. It's the same for Jupiter. In the case of the transit, that makes sense because the likelihood to be aligned and to produce a transit is very low. So that's why we don't have any there. So in terms of the mass, it's slightly better in terms of the Jupiter equivalent because the mass is quite sensitive here. We're just limited by the duration of the survey. So we have right now about 20 years of backlogs of data. So we are detecting clearly planet like Jupiter. You see plenty of planets like that. We're detecting small planet like it was the case for the transit here, but we have this kind of weird object that actually we call the hot Jupiters, whether they have the size here or the mass of about Jupiter. What is very striking for this object is they have all very short period, let's say a few days in that case. This is the period of the orbit. And this is where the whole adventure started 25 years ago with the first discovery of a planet that was exactly of that kind on the star 51 Pegasi. And that was the beginning of the race for finding planet under the stars, and I was the first one to be found. It's interesting to just compare the occurrence of each of these planets. If you look in the universe and look at all the stars in the universe, how likely do you have to just have any of these planets orbiting any of the stars? Well, when you put number, this is quite complicated number to do. You don't really see it on this diagram right away because these diagrams are the combination of different data. But if you do properly the analysis of the statistics there, what you would find is actually this very extreme object, the hot Jupiters, they're quite rare. A few percent of the star, they do have a planet. So the reason why we picked one of them is we had a sample when we started the survey of more than 100 stars. That was kind of a new approach we had compared to other teams before. They were using much smaller sample. So this is how we picked one. Actually, we had two in the sample. But what is interesting is we have about 10 to 20% of planet that seems to be like Jupiter. It's not very well defined because we don't really know exactly where to stop the mass. You are clearly seeing on this diagram that a lot of these planets seems to have a mass that is clearly more massive than Jupiter, 2, 3 times, 5 times, 10 times. So we have clearly more massive planet. We also have planet that seems to have period slightly shorter. But I mean, globally, this is the kind of planet that would qualify like similar to our Jupiter or giant planet. The big surprise is this bulk of object here. And frankly, these planets were not expected at all. I call that the gift of nature because they are really quite a lot and they are not so difficult to detect, mostly using the transit technique. So with a space transit machine like the Kepler missions, that has been really a feast of planet discoveries because it has, I mean, if you just count the number, they must have 2,000 or 3,000 of the transiting planets that have been found because they're essentially very easy to detect. When you have a planet orbiting very close to the stars, I mean, the likelihood of a transit is very high. But the funny part of it is when you look in the solar system, the only planet which is very close to the star is Mercury, and Mercury would be sitting far away compared to this object and clearly not in the mass of the Earth, much smaller. So in a sense, this planet doesn't exist in the solar systems, and we have to account for then this diversity. We call that usually planet that is Earth, super Earth, mini Neptunes, Neptune range. They are reading this range of object there, and we have to account for the reality of this planet, knowing the new formations of planetary systems. So we see our solar system is slightly different way, and that was acknowledged by the Nobel Prize Committee, that we have now recenter our solar system compared to the many others. So in a way, you could see that, or you can compare that with the time when we realized that the Earth was not at the center of the universe, but actually we were just orbiting a star. Now what we are finding here is the solar system is certainly not the archetype of the many systems that you find in the universe. It's one amongst many, and as a configuration we have so far kind of failed to really detect, and clearly for the Earth twin, because it's difficult. So we're working quite a lot to find this object, and that's certainly the next frontier, and where we're working hard right now and trying to push this discovery into the direction of this system to complete the picture, because we certainly expect planet like the Earth not to be common, but certainly not to be extremely rare. There must be other. And if you believe that the Jupiter here are telling you some part of the story, we may end up to have something like 5–10% of planet like the Earth. That's kind of the expectation, but we have to demonstrate that. And this is something that we have not done yet. Now, this situation is interesting because in some case we can combine the measurements of the mass and the size of the planet. So this is this kind of diagram that is the mass of the planet in Earth unit in log scale and the radius of the planet there. So you see the hot Jupiter, they're over there, they're slightly above in terms of a mass radius. So it means the density is less than the density of Jupiter. They kind of inflated because it's slightly hotter than Jupiter. So this is the reason why. But roughly speaking, we do have planet along this regime here. That is what you expect the density of a planet like Jupiter. You see Saturn is very similar to Jupiter in terms of structure, density. Now we have a jump when we're dealing with Neptune planet. They're denser because the gas are just heavier in this planet. The kind of model that is displayed here to give you a hint where you would be sitting, it's a planet full of water. You imagine you just made a planet entirely with water, which is not something we expect, because we expect the planet to be kind of a bit more structure with a core, heavy core, and then slightly lighter gas or material around. But they give you an idea where you would sit, and Neptune is just sitting between a giant planet with a lot of gas like hydrogen and helium, and then a planet like that would be made of water, just sitting just between the two. You do see there is quite a substantial amount of planets that are in the same regime here, that Neptune that we have picked up. And then comes the very interesting element here. When going down here, you're hitting the Earth model. This is the Earth density model. So you clearly see that one is the Earth would be there, that we do have planet that would qualify as Earth-like in terms of density or bulk density, but we also, in the same regime of object, about 5 to 10 Earth mass, we have object that with the same mass is clearly more inflated and would more qualify like a water kind of world, a water planet. And you can even kind of see there is a kind of some kind of a valley or drop in terms of density in between, which is on purpose because it happens that some of these planets has actually lost the atmosphere because they were too close to the stars. Remember, this planet or the planet I was mentioning before, they're orbiting close to the stars within 10 to 20 days, this kind of bulk of super Earth object I was mentioning. So this new picture of planet force us to revisit a little bit what we had in mind, because in the solar system, we essentially have the telluric planet here. Then we make a jump. We have the ice giants, or Neptunes belong to these ice giants. And then we have the giant planet. We have nothing in between. Actually, there is way more diversity here in between, and we have to account for this new picture of what actually is a planet. So what we have here in this system is the fact that between the ice giants and the Earth, we do have another kind of planet that we're not sure exactly what it is about, but these are certainly planets worth to be better understood, because some of them can clearly have atmosphere, very similar to the Earth, but it just may have just a complete different core, or some of them may have very deep atmosphere. You can imagine what we call ocean planet. In that case, that would be an atmosphere of maybe 2, 3, or 5,000 kilometers of water. So you can imagine the pressure you have, and the structure of the water will be very different from the one you have on the top. And then you can have some kind of mini Jupiter or something like a mini Neptune. So this is really a new world here, and also a new world with a new conditions that we can use. Remember, in astrophysics, what is pretty nice is it's as many labs as you can imagine. So the universe is a fantastic lab because you already have so many parameters that you cannot reproduce on Earth, and on the pressure, temperature, vacuums. I'm not talking about the time scale. Also, you can play with that, and in that case, we do have a diversity of planets clearly in the universe, the way more that we expected. So that happens quite a lot of possibilities. So what we could do right from that is just not sticking only on the density. We can move to the atmosphere itself of this planet. How we do that? Well, actually, when you have a transit like that, there is a time when the planet goes in front. This is the transit time that produces this slight decrease of the flux of the stars. But there's a time when the planet goes behind. It's called the eclipse. It's a very special moment where you only see the stars practically. So in terms of observations, what we do in astronomy is when you record the flux of a star along the situations, you do have a slight drop of the flux at the time of the eclipse when the planet is behind, or you have a drop, the main drop of the flux when the planet is in front, which is the time of the transit here. So if you zoom in this situation, what you have to think about is this eclipse as the time when you only see the star. So practically in your mind, what you have to figure out is the flux until that point is the flux of the star. Anything above is the planet. So when you do that, actually you measure a combination of the star and the planet. If you use that measurements to reset the amount of the stars, you get the flux of the planet. We call that the phase functions, this variability, the dark side and bright side, similar that the sphere of the moon. And the study of that in different color tell you something about the planet, the atmosphere of the planet. And if the planet has no atmosphere, this is even telling you something about the surface of the planet. So this is a way we can do way more than just getting few parameters on the system. Now, what we could do as well is we can study this moment of the transit in great detail using different wavelengths. To just display that, let's imagine that this is ISS pictures, real picture. So let's imagine in that case that we're going to produce a transit in that case, and we're going to simulate the stars and as being the moon in that case. So you have this the fact that you measure a transit, so the Earth is transiting in front of the moon. This is in the visible light, and you see the size of the atmosphere here, which is the Rayleigh scattering, which is about the blue sky that you do see. This is this effect. It's about 20 kilometers, the height of this atmosphere you do see here. Well, if you use infrared, that is practically going down to the surface, you would see the heat of the surface of the planet Earth. In that case, you won't see the atmosphere. If you pay attention to the scale, you will see a change of scale compared to before. This is the 20 kilometers has been removed, and you see really the planet itself, the bare, rocky planet is visible at that wavelength. Now you can try to look for a specific transition line, one of them being the ozone. The ozone is slightly more in the infrared. In that case, you will be measuring the extent of the ozone 8, that would be 50 kilometers, and that's why it's much thicker. You see a difference between the infrared and the ozone. So you can think about that way in many different wavelengths, and all the feature you may have into the atmosphere of this planet, and in this whole we can retrieve the atmosphere composition of planet using that kind of trick. So we need, of course, big telescopes or space telescope to do that, but we actually are measuring planet atmosphere, even if we don't see this planet, by all the tricks I was mentioning to you. Now, when you think right now about the diversity of the atmosphere, you think about the many planets that we have on other stars. So it starts to open a completely new realm of possibilities. And of course, the next question you can ask yourself is, can we say something about what's going on in terms of chemistry on this atmosphere? Can we say something about the possibility of life? And quite substantial progress has been made on that front, combining different disciplines together. It's not anymore astrophysics, so it comes now to geophysics and chemistry. And I would like to share with you some new progress on that front. Well, first, from the astrophysics perspective, we have a very simplistic way to see atmosphere of planet, or we can get, some people thought that getting oxygen will tell you the whole story and maybe there is life. Actually, we know it's not true, because you can break the oxygen from the CO or from the water. By the way, water is something very common for an astronomer. There's nothing special about water. It's very common molecules in the universe. You see water in disk, in proto-planetary disk. You point in the radio telescope, you see water everywhere. There's nothing special about water. So the oxygen, you have to be careful that sometimes the oxygen was seen as a feature, as a tracer of life. This is not the case. What you would need is essentially a combination of different molecules, and in that case, is essentially you need a copy of the Earth, or you will have to understand the global planetary conditions on the Earth. And so we are more on this concept, combining the astrophysics, planetology, and then with the atmosphere. But sticking to the life, recent progress has been made. Essentially, you may have heard about what's called the life in planet context. So some time ago, people believed that the life should be coming on the bottom of the ocean. But recently, I think this has been revisited because progress has been made on the prebiotic chemistry producing the amino acid. There's a couple of references here. This is your friend's chemist that came up with that. And what they did is essentially they've been using very common ingredients that we have when you form a planet. Water, it's kind of everywhere. As I said, if you have some volcanic activity, so you get SO2, SO3, you build these ingredients, and this is something that is needed for this prebiotic chemistry. HCN is a delivery you get in comet. This is forming quite substantially when you have a comet, icy comet. There's a lot of cometary impact early on, so there's an expectation there's a lot of HCN is falling on the planet at that time. It's not something very friendly for the life you may connect, but it's, at least for the origin of life, it seems to be critical. Nothing special of the atmosphere. We call that chemistry neutral. There is no energy in the atmosphere. The energy here that makes the chemistry comes from the UV. The UV, because there is no blocking UV, there is no ozone at that stage, and I mean, a network of chemistry, I just flip it for you, has been developed, combining these bare ingredients. The starting point is somewhere here, that seems to produce a network of chemistry that is leading to a prebiotic chemistry, at least to the amino acid, and even further down, and along the path for life. It's very exciting when you think about that, because it is connecting, in a way, lab experiment that can be tested and reaction that can be tested within a condition that could be tested. Do you have this ingredient? Can we see this ingredient into the planet? And can we guess what kind of chemistry is going to happen when we have this ingredient? It's really connecting what you see and what you can replicate and simulate at the same time, connecting to life. This is a kind of new approach, and you see this not very far away. It's just 2015. So on the top of that, what has happened as well is the perspective about looking for Earth has changed, because when you look at planet on other stars, you're looking at different time scale. You can pick up a star that is 1 billion years or 2 billion years. So you really have not to only being obsessed and focused on the life as it is today. You really have to see the whole history of life. And just to recall that the atmosphere on Earth has changed quite a lot. I mean, from the Archean Earth into the Proterozoic Earth to the modern Earth, I think we have a complete different picture. And the idea is this kind of atmospheric feature can be measured remotely by what I described before. So we should be, in a way, be able to retrieve some information of the level of the planet interaction, the planet cycling that you have, and possibly the origin of life. To give you an idea of some theory about the origin of some of these elements, depending on, how you can make it, and the feature here that we would be able, in terms of astronomy, to detect into the atmosphere. So the idea is to combine all of this, to combine the different scenarios, and hoping for the fact simply that we have so many planets to study, the diversity of the different situations we're going to face should direct us into a better understanding whether the UV is the main criteria or not, or whether we have the generation of that ingredient or not. Do we have water everywhere? Maybe we're missing water. Maybe we're missing atmosphere at all. Atmosphere is vanished. Maybe we're going to see tons of Venus, which is a complete different atmosphere where the CO2 has not been recycling. All of this we're going to do. So it's really changing completely perspective, but opening so many possibilities here to look around. Now, what is even fascinating here, we're not only going to see stuff, but we're going to bring back stuff. Well, not on exoplanet, unfortunately, they're too far away, but we're all seeing this picture. This is Mars, and we're going to bring rocks from Mars. We're going to bring a diversity of rocks. And I think this is quite a fascinating moment for the humankind when you must be expecting a lot of surprises. And you may be aware that this is the Jezero crater when we had the robot, landing, and they're going to explore, they're going to follow a path along this crater and moving from bottom to the top there. And the reason why we picked that up, I think it's pretty obvious here. If you want to build such kind of feature, you don't need to be a expert of planetology to figure out this has been created by some kind of flow of water here, and we really expect this to be the kind of the end of a river process. And we expect, depending of the layer of the water, the age of the water, there is a very fascinating diversified chemistry along the way, moving down to the bottom of the lake, to the top of to the limit to the water, and then above outside the lake. So if you have to imagine what this lake I mean, was in the past. I mean, essentially, if you go back about 4 billion years ago, that's what you would expect on Mars. And people is quite exciting because at that time, we do believe that the evolution of the Earth was a bit similar. So there is some similarity between Mars and Earth at that age, and then Mars stopped evolution because of the fact there is not anymore any more plate tectonics, and it started to move into a maybe more stable situations, or where all this is kind of frozen and left as it was, while on the Earth, of course, with the plate tectonics, everything is destroyed in a way, and we cannot access to that early moment. But we do know that life has started at that stage on Earth pretty early on. So there is certainly a hope that by getting some hint on the chemistry of Mars, we don't expect to see really, I mean, any living creature there, but we certainly expect to see interesting, I think, imprints of the chemistry that has happened in this lake, or a different location through this lake and to the outside of the lake in the past. And this is completely new because we're not going to do that remotely. Of course, it will be done remotely, but we're going to bring a lot of these rocks back on Earth with all the capability we have to study in great detail all these rocks. And that will be the next 10 to 15 years, I think, an absolute defining moment, I think, for the understanding of the origin of life in terms of chemistry process. So this is what it is. This is what we have now on our plate, and this is why I said we are kind of very excited to combine all this field together. Now, what is interesting when you talk to geophysicists, and that's where they embark with us, is the kind of time scale I've seen you, and there is some similarity in terms of geophysics on Earth at that very moment that is critical for the onset of life, and we can use I think the knowledge we have on Earth to better understand what's going on Mars. This is where the geophysics connects entirely with the geophysics as it is being studied on Earth, and the one that will be done also on Mars. So this is extrapolation. It is quite fascinating here. Now, to end with, I would like to share with you my own personal way, how I think we have to see the evolution of life and the beginning of life. For the physicists, it's kind of very simple. We define what we call the complexity. Whatever unit you think about it is how many bound, the diversity of the chemistry complexity, whatever. That is this really the complexity matter here, and there's somewhere the complexity has to grow. And we define the criteria, which is the aliveness. In a way, it's a very difficult criteria, but essentially what you have is life will build up its own process in a way. It doesn't depend anymore on outside ingredient feeding in to make it alive. I mean, this is what we're doing in terms of being alive. We're using raw product, and we're making all what we need. And so we recreate all the ingredient that we need to stay alive. In a way, this is what would define, I think, the aliveness, how far we are into this process. So people kind of believe the expectation, it's kind of not random, but it's a process which is certainly not a continuous linear flow. There must be great progress and steady, and even we can imagine going backwards at some extent, but it has to be kind of erratic process along the way until you reach some kind of alive threshold, whatever it is. But there is a point when you just go by your own. And how do we define that? Well, essentially it becomes biology. So if I move myself slightly off or maybe decrease here, we really start the evolutions, and this is where you can clearly be sure you are alive at that point. Before that, you're not completely alive, you're almost alive. And how are you going to progress there? Well, we're going to combine all these techniques that I was mentioning, all this approach I was mentioned to you, where you're combining the astrophysics inputs with the geophysics conditions where you have the beginning of life. And then this has to trigger some prebiotic chemistry, and prebiotic chemistry has to be even more alive, and by building a more macromolecule at some point getting to the evolution. So the point I'm making here is I think the new development in this field is the combination of these disciplines. I'm working now on joint project combining astrophysical perspective and data with an experiment that is being done in wet lab. So I think there is a lot of very interesting features that we should explore, and I mean I really encourage you to think a bit that way if you're interested by this topic, and to clearly have a look at what's going on Mars. This is just our last result if you are interested about this. This is a result when we have studied prebiotic chemistry under the ultraviolet conditions that I was mentioning before. And in that case, the team is really a mixed team between geophysicists, astrophysicists, and molecular biologists, where we essentially what we've done, we have built an astrophysical equipment which is simulating the sun into a wet lab, trying to measure the level of reaction or along the pathway that is right now tested. We're testing the pathway to move from these very raw ingredients into the prebiotic chemistry, essentially the amino acids here that we're testing. Right, so I hope I gave you some ideas and maybe some incentive to talk to your colleagues, physicists that are maybe interesting to that topic. And I wish you a successful meeting. Thank you very much.